Welcome, weary traveler, to the gentle embrace of Xnoesis. Tonight, we embark on a tranquil journey into the profound, exploring the deepest currents of human thought and the silent spaces that define our understanding of existence. Settle in, let your mind drift, and allow the quiet hum of cosmic mysteries to lull you into a state of serene contemplation. Our destination is not merely knowledge, but a peaceful dwelling within the boundless expanse of the unknown, preparing you for the tranquil depths of slumber. Roughly 300,000 years ago, a peculiar, even paradoxical situation began to unfold within the nascent minds of our ancient ancestors. The very ascent of their cognitive abilities, the sharpening of their intellect, the intricate weaving of neural pathways within their expanding brains was undeniably a powerful tool for survival. This burgeoning intelligence provided unprecedented advantages. It honed their skills for resolving immediate, everyday challenges. It allowed them to develop sophisticated strategies for procuring sustenance, ensuring the continuation of their lineage through successful mating, and fortifying their defenses against the myriad perils of a hostile world. The more refined and complex the brain became, the more adept it grew at constructing intricate models of reality. This advanced neural architecture permitted our ancestors to not merely react to their immediate surroundings, but to mentally project themselves into the unfolding tapestry of the future, to anticipate consequences, to plan beyond the fleeting moment. It was a remarkable evolutionary leap, granting foresight and strategic depth previously unimaginable. However, this relentless march of cognitive evolution contained within it the seeds of an unforeseen, almost cruel revelation. As the human mind continued its upward trajectory, achieving ever greater levels of sophistication and insight, it eventually reached a precipice. It became so exquisitely attuned to the patterns of existence, so adept at deciphering the rhythms of life and the inevitability of decay, that it stumbled upon a truth it was perhaps never meant to fully comprehend. A truth that, once glimpsed, could never truly be unseen. The horrifying spectacle of a fellow kinsman or kinswoman, vibrant with life one moment, then utterly still and lifeless the next, was no longer just an event to be observed with primal fear or instinctual avoidance. No, for the newly awakened human consciousness, it became a mirror. In that stark, unyielding reflection, the observer recognized a chilling, undeniable prophecy that one day, inevitably, they too would share that same fate. The vibrant spark of their own individual being would, with absolute certainty, be extinguished. And so, approximately 300,000 years ago, in a profound and perhaps most disquieting sense, the most unwelcome event in the entire sprawling history of life on Earth quietly unfolded. It was the emergence of the first living creature capable of recognizing its own existence with sufficient clarity and depth to grasp its inherent finitude. This singular moment marked a species, awakening to its own impermanence. By all indications, humans are, indeed, the solitary sentient beings known to inhabit this planet, who possess this haunting awareness of their own mortality. Any evidence suggesting otherwise, from the most rudimentary observations of animal behavior to the most advanced studies, remains, at present, profoundly unconvincing, or at least fundamentally different from our deep, abstract comprehension of ultimate cessation. On one hand, the sheer crushing weight of this understanding should, by all logical reckoning, utterly paralyze us. What conceivable purpose could there be in striving, in struggling, in carefully selecting a particular path through the labyrinth of life, if every single trajectory, every ambition, every dream, ultimately converges upon one solitary, inescapable destination, the silent, echoing expanse of the grave? The sheer absurdity of effort in the face of absolute nothingness, ought to drain all meaning, all motivation from our endeavors, leaving us as motionless as statues carved from despair. Yet consider our astonishing persistence. Take a moment to reflect upon the enduring marvel that is humanity. We are still here. We have not succumbed to the all-consuming despair. We have not collectively withered away into extinction, nor have we regressed to a more primal and perhaps more comfortably ignorant level of reality perception. How, then, is such a profound contradiction even remotely possible? What fundamental mechanisms of adaptation, what intricate psychological defenses, what deeply woven cultural narratives could have possibly evolved within such a relatively brief span of evolutionary time to enable a species to grapple with and continually overcome the crushing existential anxiety born from the undeniable awareness of its own inescapable death? In essence, the core question that quietly reverberates through the chambers of our collective consciousness, and the very subject we shall gently explore tonight, is this: how do we, as a species and as individuals, manage to convince ourselves, day after day, year after year, to persist in living, to find meaning, to strive, to love, to create, to dream, even when confronted by the omnipresent, unyielding shadow of the inevitable? This is the paradox, the mystery, and the enduring strength of the human spirit. In the year 1973, an American anthropologist of towering intellect and profound insight, Ernest Becker, unveiled a seminal work that would, just 12 months later, be honored with the prestigious Pulitzer Prize. This extraordinary book laid the foundational cornerstone for what would become known as terror management theory, a framework attempting to understand human behavior through the lens of our inherent fear of death. The book, strikingly titled The Denial of Death, posited a radical yet compelling argument. According to Becker, the denial of death is not merely a psychological quirk. Rather, it represents the single most potent and adaptive mechanism that conscious beings like ourselves have managed to evolve and solidify within the remarkably brief span of our existence. This mechanism allows us to navigate the terrifying awareness of our finitude without succumbing to utter incapacitation. Within the pages of this groundbreaking work, Becker advanced the hypothesis that a substantial, perhaps even overwhelming portion of human culture, in all its variegated forms and expressions, is, at its deepest and most fundamental level, a complex and often unconscious edifice built upon the urgent need to overcome the pervasive fear and anxiety evoked by each individual's understanding of their inevitable end. It is a monumental collective effort to erect psychological and social structures that either directly or indirectly shield us from the full, unmitigated horror of our own non-existence. Consider the implications. If an individual were to fully acknowledge and internalize the absolute, unyielding truth that they possess no control whatsoever over death, that it lurks, a silent predator, at every turn, in every shadow, around every corner of their brief temporal existence, and if they were to permit this chilling realization to fully occupy and consume the entirety of their conscious mind, the consequences would be catastrophic. They would inevitably plunge into such an abyss of fear and trembling, such an overwhelming deluge of existential dread, that they would find themselves teetering precariously on the very precipice of madness. Ernest Becker's observations resonate with grim psychological realities. For instance, individuals condemned to capital punishment, awaiting the grim execution of their sentence, frequently exhibit a dramatically elevated risk of developing psychotic delusions. This deeply disturbing phenomenon is one of the most stark manifestations of what is chillingly referred to as, quote, death row syndrome. The mind, pushed to its absolute limits by the inescapable certainty of its impending annihilation, resorts to extreme, desperate measures to construct an alternative reality, however fractured or delusional, rather than confront the unbearable truth. This psychological insight carries a profound, albeit disquieting, implication for humanity's collective future. It suggests that there is a high, perhaps even overwhelming probability that, as a species, we may find ourselves absolutely defenseless when confronted with virtually any profound existential threat that extends beyond our immediate personal mortality. To illustrate this point, imagine a scenario where, tomorrow, we receive irrefutable scientific confirmation that a colossal meteor is irrevocably destined to collide with Earth in just 5 years, or that a superintelligent artificial intelligence, unleashed beyond our control, will eradicate humanity within 2 decades, or that the most catastrophic consequences of global warming will irrevocably transform our planet within 50 years. Even with such dire, well-substantiated warnings, it is highly probable that we would, as a global civilization, be largely incapable of taking the necessary decisive actions to avert these impending disasters. This incapacitation would persist even under the astonishing condition that, objectively speaking, we could indeed do something to alter our fate. The reason, according to Becker's framework, lies deep within our adaptive programming. To constantly ruminate upon an abstract, large-scale, and seemingly unpreventable threat of collective death is simply not an adaptive survival strategy. Our minds are wired to deny, to deflect, to rationalize, to prioritize the immediate, the tangible, the controllable, rather than to dwell endlessly on an impending doom that, from a personal perspective, feels distant, abstract, and utterly beyond our individual agency. This inherent psychological mechanism, while protecting us from individual madness in the face of our personal death, paradoxically leaves us vulnerable to collective inaction in the face of larger, species-level threats. Among the myriad ways humanity has devised to deny its own mortality, a pervasive and enduring mechanism, though certainly not the only one, is the deeply ingrained belief in an afterlife. Billions of individuals across diverse cultures and throughout recorded history have, in some form or another, clung to the conviction that life extends beyond the threshold of physical death. This belief manifests in countless permutations, from ethereal heavens and fiery hells to cycles of reincarnation and the tranquil embrace of ancestral spirits. Many within the contemporary scientific and secular communities frequently assert that the remarkable advancements of modern science have irrevocably dismantled the very concept of an afterlife, rendering it an outdated relic of less enlightened times. However, this assertion, while carrying a veneer of empirical certainty, is, at best, only partially accurate. To speak with absolute candor, the very nature of scientific inquiry, which relies on empirical observation, falsifiable hypotheses, and repeatable experimentation, inherently limits its scope. Science, by its methodological design, cannot definitively rule out every conceivable human-conceived variant of what might be termed post-mortem experience. How can one experimentally falsify a realm that, by definition, exists beyond the reach of our physical instruments, beyond the confines of our measurable space-time, or within dimensions we have yet to even conceptualize? Indeed, rather than unequivocally debunking all such notions, science itself, in its relentless probing of the universe's deepest mysteries, occasionally presents us with intriguing, albeit highly speculative, ideas that touch upon themes reminiscent of an enduring consciousness. One such captivating concept, born from the most cutting-edge frontiers of theoretical physics, is known as, quote, quantum immortality. Quantum immortality is a direct, if highly provocative consequence stemming from one of the most radical and mind-bending interpretations of quantum mechanics, the many worlds interpretation. This particular interpretation, a concept that asks us to fundamentally rethink the nature of reality, postulates the existence of a vast, perhaps infinite, multiverse, where every possible outcome of every quantum event actually occurs in its own distinct, branching universe. This groundbreaking interpretation was originally put forth by a brilliant and, as you might infer, profoundly influential physicist named Hugh Everett III, whose revolutionary insights continue to reverberate through the world of theoretical physics. Quantum immortality, then, presents an extraordinarily extreme, indeed almost unsettling, method to theoretically demonstrate the existence of these multitudinous parallel universes. It is a thought experiment so stark in its implications that I must emphatically caution against any attempt to replicate it in your own home or, frankly, anywhere else. To describe it crudely and in the simplest of terms, it reimagines the famous thought experiment involving Schrödinger's cat, but with a chilling modification. Instead of a cat confined within a box, the experimenter themselves is placed in the cat's perilous position. In the hypothetical experiment proposed, a firearm is aimed directly at the participant's head. The crucial element is that whether this firearm discharges or not is contingent upon the spontaneous decay of a single radioactive atom. The probability of this atom decaying within a given time frame is set at precisely 50%. Consequently, the risk that the firearm will discharge and the participant will tragically perish as a result of the experiment is exactly 1 in 2. Now, here is where the many worlds interpretation, as conceived by Everett, comes into play. If this interpretation holds true, then at the precise moment, the radioactive atom either decays or does not decay. That is, at the instant the quantum choice is made, the universe does not merely observe a single outcome. Instead, it instantaneously bifurcates or splits into 2 distinct parallel universes. In one of these newly formed universes, the participant remains alive, the firearm having failed to discharge. In the other, tragically, the participant perishes. But for the conscious observer, the implications are profoundly different. From the singular point of view of the surviving observer, the splitting of the universe is not perceived. We, as conscious entities, do not possess any experiential mechanism to detect or register the creation of these parallel branches. Furthermore, and crucially, we cannot have the experience of non-existence. The very concept of experiencing our own death or non-being is, in a profound sense, a logical contradiction from the first-person perspective. Therefore, according to quantum immortality, there is only ever the viewpoint of the survivor. For this eternally surviving observer, the experiment would, from their subjective experience, continue to repeat itself again and again for an arbitrarily long duration, never, ever culminating in their death. Imagine the sheer incredulity and eventual exhilaration. When such an experimenter survives 10 consecutive rounds, they might exclaim, "By Jove, Hugh Everett was absolutely correct," because the statistical probability of surviving 10 consecutive trials, where each trial has a 50% chance of death, is a mere 1 in 1024. The odds, from a classical perspective, are already astonishingly slim. But if the experimenter were to survive 100 consecutive attempts, the possibility that anyone in their particular universe would retain any lingering doubts about the veracity of quantum immortality would become virtually non-existent. The statistical probability of such an outcome plummets to a minuscule 1 in a number so astronomically vast that it defies easy verbalization. A 1 followed by 30 zeros, a number so small it renders conventional intuition meaningless. However, to reason with a slightly more rigorous precision, the universe during such an experiment doesn't merely divide into two stark alternatives. The branching is far more intricate, far more subtly nuanced. There would be universes where the firearm did discharge, but the experimenter experienced an unforeseen muscle spasm, causing them to narrowly evade the projectile. There would be universes where the mechanism of the firearm simply misfired, a manufacturing defect or a quantum anomaly preventing the bullet's propulsion. There could even be universes where the very atoms comprising the bullet, by a fantastically improbable quantum fluke, synchronously scattered in myriad directions, causing the projectile to disintegrate harmlessly before it could ever make contact with the observer's head. Extending this line of reasoning even further, one could contend that in the tapestry of real life, the probability of death at any single, specific moment in time can never times truly equate to a perfect 100%. Even in the cataclysmic epicenter of a nuclear detonation, while the overwhelming, almost infinite majority of universes would witness the immediate and total annihilation of the observer, there would always remain an infinitesimally thin stratum of universes, a delicate, shimmering layer of possibility in which some unimaginably improbable event transpires, allowing the observer to remain alive. And consequently, by this logic, the conscious observer possesses a form of personal, subjective immortality. Now, if your initial reaction to this concept was one of awe or excitement, suggesting that this sounds cool, I invite you to delve a little deeper into its chilling implications. For this theory, in its stark reality, does not guarantee that the conscious observer, this eternally surviving version of you, must necessarily remain fully healthy or even coherent throughout this perpetual existence. Indeed, a direct and horrific consequence of quantum immortality would be the creation of a personalized, inescapable hell. In this terrifying scenario, the individual would be utterly incapable of dying, regardless of the unimaginable depths of their suffering or the grotesque mutilations inflicted upon their form. Given that the probability of death at any subsequent moment in time can never be 100%, this individual would, from their own subjective experience, eventually outlive every other human being on Earth. They would witness the slow, agonizing transformation of our sun into a red giant, the eventual fiery consumption of our planet. They would, in the end, remain as the last bastion of consciousness, an eternally drifting, tormented mind, cast adrift in the boundless, indifferent expanse of a dying universe. It sounds like absolute madness, a chaotic symphony of absurdity, does it not? Yet, within the rigorous, if discomfiting, logical framework of the many worlds interpretation of quantum mechanics, these are merely the unavoidable, terrifying consequences. Therefore, we ought to find some measure of comfort in the understanding that the very existence of these multitudinous universes remains, at its core, a profound hypothesis, a theoretical construct that has yet to receive definitive empirical validation. Furthermore, even within the confines of the thought experiment itself, there exist a myriad of intricate nuances, conceptual ambiguities, and significant gaps in our current understanding. For instance, the prominent physicist Sean Carroll astutely raises a crucial point. It is not at all a foregone conclusion that the surviving version of you would, in fact, still be you asterisk in the fullest sense, rather than merely a kind of cosmic twin or an identical copy. Though, it must be acknowledged, the precise philosophical distinctions surrounding personal identity might offer little solace to those endlessly surviving copies, eternally adrift in their isolated realities. The life and work of Hugh Everett III, the visionary who first proposed the radical idea of the multiverse, were meticulously chronicled by the Russian historian Evgeny Shchikov. Shchikov's biographical sketch reveals a fascinating tension in Everett's personal beliefs. Everett, despite his profound scientific contributions, was a staunch atheist, firmly convinced that his groundbreaking theory of multiple worlds offered him, personally, a guarantee of immortality. His consciousness, he asserted, was bound, at every branching point of the universe, to follow any path that did not lead to his demise, continuing thus, infinitely, into eternity. Perhaps it was this extraordinary conviction that led Everett to cultivate what many would consider a profoundly unconventional, almost self-destructive lifestyle. He famously eschewed medical care entirely, indulging in prodigious meals, smoking 3 packs of cigarettes a day, and consuming alcohol with an alarming lack of moderation. He never once engaged in any form of physical exercise. And so, it was, at the relatively young age of 51, that Hugh Everett III departed this world, at least in the particular universe we currently inhabit. The stark irony of his life and death, juxtaposed with his theory of personal immortality, serves as a poignant, if dark, commentary on the human relationship with finitude. The narrative takes an even more somber turn when, in 1996, his daughter, Elizabeth, tragically took her own life through an overdose of sleeping pills. In her handbag, she left a heart-wrenching note stating her intention to join her father in another universe. A testament, perhaps, to the enduring power of a father's theories, even when they offer a chilling and uncertain form of solace. But regardless of the elaborate conceptual frameworks we construct, regardless of the intricate stories we weave for ourselves, and no matter how ingeniously we strive to deny, to deflect, or to rationalize away our own inherent finitude, there always remains the stark, unvarnished possibility that death will, in fact, deliver precisely what we, with every fiber of our being, endeavor to avoid contemplating. That death is simply the end. That on the other side of that final threshold, nothing awaits us. A complete and utter void. Yet even to speak of nothing in this manner can feel like a contradiction, as the ancient Eleatic philosopher Parmenides famously declared that it is impossible to reason about that which does not exist, thereby, in a paradoxical twist, violating his own profound instruction by daring to articulate the concept of nothingness itself. But it is precisely this nothing that we shall now venture to explore, delving into its shadowy depths. Many individuals, even those who may not subscribe to the vivid imagery of a punitive hell, nevertheless regard nothingness with an equivalent, if not greater, degree of profound dread. Nothingness dogs the heels of being, wrote Jean-Paul Sartre in his monumental and weighty philosophical treatise, Being and Nothingness. A fellow traveler in the vast landscape of existential thought, the philosopher Martin Heidegger was reportedly seized by a profound, almost visceral horror at the mere contemplation of nothingness, dedicating a considerable number of pages to his own intricate ponderings on this elusive concept. However, I would suggest that the death of a human being, the individual cessation of consciousness, represents merely a faint echo, a weak, localized manifestation of a much more fundamental, much more all-encompassing, and arguably more terrifying form of nothingness. Therefore, tonight, I propose we elevate our contemplation to a more foundational plane. Let us speak of that profound nothing, from which, astonishingly, the entirety of our known universe, in all its staggering complexity and grandeur, is believed to have emerged. You might reasonably inquire, but what, precisely, can one say about nothing? The answer, as it turns out, is a surprising abundance. Enough, in fact, to fill the pages of two distinct best-selling books by different, yet equally eminent, authors. One of these authors you will almost certainly recognize, the theoretical physicist and cosmologist, Lawrence Krauss, whose work has profoundly shaped our modern understanding of the universe's origins. The second is a sharp scientific journalist, a discerning critic, and a man whose intellectual demeanor, some might observe, bears a striking, if superficial, resemblance to a certain brilliant but acerbic fictional diagnostician, Jim Holt. The relationship between these two intellectual titans, though marked by mutual respect, also carried an undercurrent of lively academic friction. Imagine the scene. One might playfully assert, "Jim, I simply want to say, you are profoundly uninformed on this matter." To which the other might retort with an equally spirited challenge, "I believe, my friend, that you tend to view these fundamental laws of nature, particularly those of quantum field theory, as almost divine pronouncements. And so, I am compelled to suggest you are, shall we say, insufficiently enlightened on this particular point." Now, while our current exploration is undoubtedly inspired by the fascinating discourse surrounding Lawrence Krauss's work, it is, in fact, more deeply rooted in the captivating narrative and expansive philosophical inquiry presented in Jim Holt's book. Why, you might wonder, this particular emphasis? Well, Lawrence Krauss, for the most part, meticulously chronicles the scientific evolution of our universe from its initial, primordial moment. And, with refreshing intellectual honesty, he candidly acknowledges at the conclusion of his work that his primary endeavor was not to seek an answer to the question of what, if anything, might have existed prior to that very initial moment of being. Jim Holt, on the other hand, embarks upon an altogether different and arguably more audacious quest. He truly delves into the vast ocean of literature, grappling with fundamental questions that transcend the purely empirical. He meticulously reflects, he thoughtfully synthesizes, and he embarks on a series of illuminating interviews with many of the most celebrated physicists, philosophers, and mathematicians of our era. His tireless efforts are all directed towards one overarching, tantalizing goal: to draw ever closer to an answer to the fundamental question, why does something exist instead of nothing? And, most importantly, as you immerse yourself in the journey of his book, a profound realization begins to dawn that nature, as we currently comprehend it, and even the traditional concept of a divine creator, are not the sole suspects in this grand cosmic mystery. By the time our discourse tonight gently draws to a close, you may well find yourself thoroughly convinced of this astonishing truth. Why does something exist instead of nothing? This question, to some, might initially appear simplistic, perhaps even childish, unworthy of serious intellectual engagement. Yet, for the polymathic mind of Gottfried Leibniz, for example, it was anything but trivial. It was Leibniz, the extraordinary individual who, concurrently with Isaac Newton and entirely independently, conceived and developed differential and integral calculus, thereby revolutionizing mathematics. It was this same Leibniz who, single-handedly, spearheaded a revolution in the field of formal logic, and who, by any measure, stands as one of the most prodigious intellects of all recorded history. And it was this very same Leibniz who, in the year 1714, first posed this deceptively simple, yet infinitely profound question to the world. Later, the renowned philosopher Arthur Schopenhauer, with his characteristic bluntness, famously declared, "Those who are not interested in the question of being, the question of world being, suffer from intellectual weakness." This highlights the enduring philosophical weight attributed to this inquiry. Even Stephen Hawking, in his seminal work, A Brief History of Time, acknowledged the profound nature of this enigma. He mused, "Even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe?" The traditional scientific approach, which primarily involves the meticulous construction of mathematical models to describe and predict phenomena, finds itself inherently constrained when confronted with such questions. It cannot, by its very nature, adequately address why the universe described by its models should exist at all, or why the universe bothers to exist in the first place. Even Ludwig Wittgenstein, whose famously terse yet deeply influential philosophical work of the 20th century, Tractatus Logico-Philosophicus, concludes with the widely recognized dictum, "Whereof one cannot speak, thereof one must be silent," found himself grappling with the ineffable. Not long before articulating that ultimate pronouncement, Wittgenstein himself wrote, "The mystical is not how the world is, but that it is." Some might readily dismiss this inquiry as overly philosophical, a venture into speculative metaphysics best left to armchair thinkers. However, even Albert Einstein, a paragon of scientific rigor, held the conviction that in humanity's earnest attempts to comprehend the fundamental nature of reality, science must walk hand in hand with philosophy. Einstein articulated this perspective with profound clarity. "A great many people, and even professional scientists, seem to me like someone who has seen thousands of trees but has never seen a forest." A knowledge of the historical and philosophical background gives that kind of independence from the prejudices of his generation from which most scientists suffer. This independence, created by philosophical insight, is, in my opinion, the mark of distinction between a mere artisan or specialist and a real seeker after truth. His words underscore the importance of a broader intellectual perspective, one that transcends the narrow confines of specialized knowledge to embrace the fundamental questions that animate all inquiry. For those who contend that the question "why does something exist instead of nothing" is inherently meaningless, fundamentally unresolvable, and thus unworthy of serious contemplation, it serves as a powerful reminder to recall the initial reception of a seemingly equally intractable question. The inquiry into what constitutes matter was first posed over 2.5 millennia ago by Thales of Miletus and other pre-Socratic thinkers. At that nascent stage of philosophical and scientific thought, this question would have seemed no more sensible, no more empirically addressable, than the question concerning the very existence of being itself. Yet, as the Oxford philosopher Timothy Williamson aptly observed, the pre-Socratics, in their audacious curiosity, posed one of the best questions ever asked. It was a question that, through centuries of arduous, often tortuous attempts to answer it, ultimately spurred the incremental development and eventual flourishing of modern science. Similarly, one could have once summarily dismissed the philosophical question concerning the fundamental distinction between animate and inanimate matter as an unresolvable enigma. Yet, our profound understanding of this very distinction, a clarity we now possess, has largely been bestowed upon us through the meticulous advancements of molecular biology. The seemingly impossible task of constructing a conceptual bridge from the finite to the infinite, a bridge that today we confidently traverse under the banner of mathematical set theory, was once widely regarded as an utterly unattainable feat of intellectual engineering. In our present era, scientists are engaged in the ambitious and painstaking endeavor of attempting to unify the realms of mind and matter, to forge a coherent understanding of their profound interplay. Concurrently, they are tirelessly working to develop a unified field theory, an overarching framework capable of seamlessly integrating matter with the intricate elegance of mathematics. As these monumental unifications gradually unfold, As our understanding deepens and our conceptual tools become more refined, it is not unreasonable to hope that we might, just might, begin to discern the faint, shimmering contours of a bridge, a conceptual pathway, spanning the seemingly unfathomable chasm between nothingness and somethingness. Now, I invite you to join me in a fascinating thought experiment. Imagine, if you will, that you close your eyes gently, and simultaneously you block out all external sounds, fully immersing yourself in a profound, imagined silence. Within this self-created void, you then attempt, with a deliberate and focused act of will, to systematically erase from your mind's eye every conceivable entity, people, plants, the earth beneath your feet, the vast expanse of the sky, indeed, everything. Visualize, with an almost agonizing clarity, the gradual disappearance of the sun, the distant stars, the countless galaxies, until all that remains is an unbroken, impenetrable darkness, a vast, echoing emptiness. Could you, by such a rigorous mental exercise, truly conceive of nothingness in its absolute, unadulterated form? When the French philosopher Henri Bergson, a master of intuition and deep psychological insight, embarked upon this very same mental experiment, he discovered a profound, almost unsettling truth. He found that even as he diligently stripped away every layer of perceived reality, every last vestige of the external world, something stubbornly, undeniably remained: his own conscious self, persisting in that very act of attempting to conjure emptiness. As Bergson elegantly articulated, "At the very moment my consciousness is extinguished, another lights up, or, rather, it is already aflame, having arisen an instant earlier, to observe the disappearance of the first." Bergson's conclusion was stark and absolute. It is fundamentally impossible for us, as conscious beings, to truly imagine absolute nothingness, precisely because some irreducible remnant of consciousness inevitably creeps into that conceived darkness, much like a persistent sliver of light persistently seeping beneath a closed door. Therefore, he concluded with profound conviction, nothingness is impossible. If, indeed, our human imagination is inherently incapable of conceiving of true nothingness, does this fundamental limitation imply, by some deeper logical necessity, that something must, by its very nature, always exist? Consider this: the universe, in its boundless and often counterintuitive reality, not only permits the existence of, but is, in fact, abundantly populated by phenomena that lie far beyond the immediate grasp of our imaginative capabilities. Let me offer a concrete example. Can you, with true mental clarity, visualize an object that possesses absolutely no color whatsoever? And by this, I do not mean an object that is merely transparent. I mean an entity utterly devoid of any chromatic property. Take a moment to truly ponder this. It is, for most, an impossible feat of imagination, yet atoms, for instance, in their fundamental essence, are precisely that, colorless. They do not intrinsically possess the property of color, which is an emergent phenomenon of light interacting with complex structures. Furthermore, the vast majority of us, with the rare exception of a select few, uniquely gifted mathematical minds, find it utterly impossible to mentally conceive of the very fabric of curved spacetime. This is the intricate, warped geometry within which, according to Albert Einstein's groundbreaking general theory of relativity, we are, in fact, all immersed and continually navigating. This theoretical construct, this fundamental warp in the universe, profoundly violates the familiar tenets of Euclidean geometry, those seemingly self-evident truths of parallel lines and perfect triangles that define our intuitive understanding of space. Indeed, for Immanuel Kant, the preeminent philosopher, the very notion of such non-Euclidean geometries was considered unimaginable, and therefore, for deep philosophical reasons, deemed utterly impossible. Yet, here we are, existing within such a reality. You might concede, all right, let's set aside the limitations of our human imagination. But what if we were to attempt to achieve nothingness under stringent laboratory conditions? What if, for example, we were to delineate a specific region of space, and then, with the most advanced technological means at our disposal, endeavor to meticulously extract every single particle of matter and every last quantum of energy from within that enclosed volume? This, to a certain degree, is indeed a feasible undertaking. Scientists can create incredibly powerful vacuums. However, at a crucial point in this meticulous process of evacuation, an event would inevitably occur, an event so profoundly counterintuitive that it appears to defy all conventional common sense. Namely, something would spontaneously, irrepressibly emerge. This emergent something is what physicists refer to as the Higgs field. And, critically, this Higgs field, once it has manifested, cannot be removed, cannot be fully evacuated. This is because the contribution of the Higgs field to the overall energy density of that very region of space we are so diligently striving to empty is, remarkably, a negative nice value. Therefore, to fully grasp the profound implication, the Higgs field represents a form of somethingness that, astonishingly, contains return-less energy than nothingness itself. Lawrence Krauss's influential book garnered a considerable share of criticism, precisely because when he asserts that nothing is, in fact, already something, he is frequently lampooned for what critics perceive as an incorrect, even misleading, use of language. However, for Krauss, his definition of nothing is a state of being where there are no particles whatsoever, and all fundamental mathematical fields are precisely equal to zero. And it is precisely such a state that, within the robust framework of modern physical models, is demonstrably impossible to achieve. This impossibility stems directly from the venerable Heisenberg uncertainty principle, which unequivocally dictates that if we possess an exact and precise knowledge of the value of a field at a particular point, then the rate of its change, its fluctuation, becomes entirely indeterminate, meaning it cannot, by its very nature, be precisely zero. When you endeavor to meticulously construct such a nothingness, something, some inherent quantum fluctuation, will, without fail, inevitably materialize within it. Therefore, Krauss boldly asserts that this scientifically defined nothing is inherently unstable. From such an unstable nothing, he argues, an entire universe could, theoretically, emerge. This startling notion that the universe itself might be a quantum fluctuation was first voiced, quite famously, in 1969 by a physicist from New York named Ed Tryon. Reportedly, while lost in thought, perhaps daydreaming, during a lecture, Tryon suddenly blurted out this audacious idea. Legend has it that several Nobel laureates present in the audience erupted into peals of laughter. Yet today, as you might well appreciate, numerous respected physicists consider this very idea with profound seriousness. And if the possibility of an entire universe spontaneously materializing from a state of zero energy does not sufficiently astonish you, then consider the recollections of the physicist George Gamow. When he recounted this very idea to Albert Einstein during a leisurely stroll in Princeton, the renowned physicist was, in Gamow's words, stunned and stopped dead in his tracks. And since we were just crossing the street, several cars were forced to stop to avoid running us over. Such was the power of the concept to momentarily halt even the greatest minds. An absolute nothingness, a void so complete that it lacks even the stage upon which nothing could happen, may indeed initially appear as a conceptual absurdity, an internal contradiction. However, from the rigorous perspective of pure logic, such a state is not inherently absurd. It is entirely possible, logically speaking, for a world to exist where there is, quite literally, nothing at all. When we speak of this world, in quotation marks, we are not referring to some object or entity, but rather to one of the myriad possible configurations or eventualities of reality. This particular world would be utterly devoid of space, devoid of time, devoid of fields, lacking even the faintest glimmer of a stage upon which any form of non-existence might play out. It would be pure, unadulterated absence, and you know what? The universe, in its fundamental essence, should be precisely this way. Why? Because nothingness represents the simplest, the most parsimonious of all conceivable realities. Gottfried Leibniz was among the first profound thinkers to articulate this crucial insight. You might question, so what if it's the simplest? The answer lies in the profound value that simplicity holds within the rigorous pursuit of scientific understanding. We have even formalized this appreciation into a guiding philosophical principle known as Occam's razor, which postulates that when confronted with competing theoretical explanations for a phenomenon, the scientist, the rational inquirer, ought to select the simpler one. And this preference for simplicity is not merely aesthetic, not merely because simpler theories are often perceived as more elegant or are easier to manipulate. No, the fundamental reason is that simpler theories are, quite simply, more probable. Consider, for instance, the historical divergence between Isaac Newton and Pierre-Simon Laplace. Newton, in his grand mechanistic universe, posited that God, the divine artificer, occasionally had to intervene to subtly tweak the orbital trajectories of the planets from time to time, lest they veer off course and collide with one another, jeopardizing the cosmic clockwork. Then came Laplace, who, with characteristic intellectual boldness, presented a compelling alternative. He famously declared that God was a superfluous entity within the elegant equations of celestial mechanics. The laws of physics themselves, he argued, precisely and efficiently accounted for the sustained stability of the solar system, requiring no divine course correction. Even if one holds a profound belief in a divine creator, one would still, more likely than not, find themselves aligning with Laplace's perspective, for his explanation represents the more probable, the more parsimonious, and ultimately the more robust solution. It introduces fewer arbitrary assumptions. However, if you are a person of faith, you might argue that it was precisely the Creator who established these fundamental laws to begin with. In that case, would it not be simpler, then, to explain everything through the direct invocation of a divine being? The prominent English evolutionary biologist and fervent atheist Richard Dawkins offers a forceful counter-argument. He contends that the postulate of a God who meticulously crafted the world is inherently flawed from the outset. As he articulates, any God capable of creating a universe and then accurately and providentially fine-tuning it for the emergence of our life must be an incredibly complex entity, the existence of which is more difficult to explain than the original problem itself. Therefore, by the principle of parsimony, the simplest of all possible theories, the most fundamentally probable reality is that of complete emptiness. In this theory of nothingness, there are no laws to uphold, no entities to maintain, no arbitrary assumptions to justify. If, indeed, simplicity serves as a reliable indicator of truth, then the theory of nothingness, in its unadorned elegance, stands as the most overwhelmingly probable state of affairs. And yet it is at this very juncture that one of the most formidable and vociferous philosophers of science, Adolf Grunbaum, steps onto the intellectual stage. Grunbaum, by all accounts, held an almost visceral aversion to the question, why does something exist instead of nothing? He dismissed it as a pseudo-problem, and those who dared to ask it he derided as not merely unintelligent, but stupid beyond belief. In stark contrast to the intellectual awe expressed by Leibniz and Schopenhauer, the profound contemplation of Wittgenstein and Heidegger, the critical insights of Dawkins and Hawking, and indeed the introspective musings of Proust, along with a multitude of contemporary philosophers, scientists, theologians, and virtually any thoughtful individual, Grunbaum perceived absolutely nothing remarkable or surprising in the mere fact of the world's existence. He was utterly convinced that there was simply no cause for wonderment. Grunbaum would argue with a dismissive air, "Some scientists and philosophers gape at the world, exclaiming, 'We know that simpler theories are more likely to be closer to the truth, but these are merely their own psychological complexes, their own heuristic shortcuts for navigating the real world. They bear no genuine relationship to the fundamental reality itself.' Consider the history of chemistry," he might suggest. In antiquity, Thales of Miletus, in his quest for elemental simplicity, believed that all chemistry could be reduced to a single fundamental element: water. When it comes to sheer parsimony, Thales' theory unequivocally triumphs in a head-to-head battle against the intricate polychemical models of modern chemistry, with its vast array of elements, compounds, and complex interactions. Yet, it is the more complex, the less simple modern chemical understanding that demonstrably corresponds to the actual reality of the world. Simplicity, in his view, is not necessarily an arbiter of truth. On another front, we are acutely aware that approximately 13.8 billion years have elapsed since the monumental event known as the Big Bang. A widely held perspective, almost universally accepted within certain circles, is that prior to this cosmic genesis, the universe simply did not exist. Is this not, then, the very definition of nothingness? However, Grunbaum would vehemently counter this notion. He would assert that the finite nature of the universe's past, its definite beginning in time, carries absolutely no bearing on the question of a primordial nothingness. Physics, he would contend, does not grant us the license to extrapolate backwards in time, beyond the singularity, and then unequivocally declare that nothing existed before it. This, Grunbaum states with unwavering conviction, is a fundamental error committed by many of my intellectual adversaries. They mentally project themselves back to the initial singularity, imagining themselves as conscious observers endowed with memory. And this projection imbues them with an irresistible, yet entirely misleading sensation that there must have been earlier moments in time. However, the Big Bang model itself, if properly understood, instructs us that no such thing as time existed prior to its inception. For Adolf Grunbaum, the very question presupposed a flawed understanding of time itself. But is this truly the case? How, precisely, does a universe come into being? Andrei Linde, a distinguished Russian physicist who emigrated to the United States in 1990 and who has made some of the most profound and significant contributions to our understanding of the origin of our universe, offers a startling perspective. According to his highly influential inflationary model, how much matter, he asks, does one truly need to initiate the genesis of an entirely new universe? A universe that would eventually come to contain billions upon billions of galaxies, each mirroring the vast celestial structures we currently observe in our own cosmic neighborhood. The answer, he suggests, is something that defies conventional intuition, something almost impossible to fully grasp mentally. To give rise to a new universe, to, in effect, boot up its own temporal dimension from a nascent 0 point, a mere thousandth of a gram of matter is theoretically sufficient. To put this in a more relatable context, a single ant's leg weighs more than this minuscule amount. This infinitesimal speck, this whisper of matter, would be enough to create a tiny, self-contained fragment of vacuum, which would then rapidly expand into the grand cataclysm we call the Big Bang. Theoretically, Linde postulates, we could orchestrate this entire cosmic genesis within the confines of a sophisticated laboratory, thereby officially assuming the mantle of gods in the most literal sense. And there exists, he cautions, no inherent guarantee that our very own universe did not originate in precisely such a fashion, birthed by a civilization whose technological and scientific development was, perhaps, not so unimaginably far advanced from our own. One might be inclined to think that such a monumental undertaking, the creation of an entirely new universe, would be entirely too perilous, too morally fraught for any civilization to attempt. The concern, naturally, would be that the newly created universe, in its explosive expansion, would inevitably consume and destroy the parent universe from which it sprang, annihilating everything in its path. However, Linde offers a reassuring, if mind-bending, counter-argument. Such a catastrophic danger, he asserts, simply does not exist. The newly formed universe, in its rapid growth, would expand into itself. Its internal spacetime would be so profoundly curved, so intrinsically folded, that from the perspective of its creator in the parent universe, it would appear as an unimaginably tiny entity, perhaps no larger than an elementary particle. Indeed, Linde suggests that, in the fullness of cosmic time, this nascent universe might even entirely vanish from its progenitor world, disappearing without a trace. In a candid conversation with Jim Holt, Linde went even further, musing on the possibilities of inter-universal communication. He suggested that a being who created such a universe would likely have only one viable method of transmitting a message, however subtle, to its potential inhabitants. The creator, Linde theorized, could exert an influence upon the nascent universe's primordial embryo, in such a way as to precisely define certain fundamental physical parameters of the newly created world. For example, the creator could meticulously set the precise ratio between the masses of the electron and the proton. Such numerical values, known as fundamental physical constants, appear from our current vantage point to be utterly arbitrary, almost accidental. There seems to be no inherent visible reason why they must possess the exact values they do, rather than any other conceivable configuration. Consider, for instance, the precise strength of gravity in our universe, defined by a number like 6.674 multiplied by 10 to the power of -11. By fixing specific values for these fundamental constants, the creator could, in effect, embed a subtle, perhaps even subliminal message within the very fabric of the universe itself. And this message, Linde Riley observes, could only be deciphered and understood by physicists. If you wish, he offers, consider this a joke. However, the profound implications are not to be dismissed lightly, for such a hypothesis cannot be entirely excluded. It offers a tantalizing, if unsettling, explanation for why the world we inhabit appears so peculiar, so idiosyncratic, and so far from any intuitive notion of perfection. Apparently, André Linde concludes with a provocative flourish, our universe was created not by God, but by a hacker physicist. Currently, the prevailing scientific consensus holds that the new inflationary cosmology offers the most compelling and robust explanation for the Big Bang. According to this profound theory, the cataclysmic explosions that give rise to universes, much like our own Big Bang, are not singular, isolated events. Rather, they occur with a surprising degree of frequency, a common phenomenon in the grand cosmic tapestry. Indeed, It would be exceptionally peculiar if the Big Bang, that momentous genesis, came with a celestial label declaring, "This mechanism operates only once." In essence, inflationary cosmology posits that our universe did not emerge from an absolute void, but rather from the existing spacetime of a pre-existing, larger universe. Consequently, our universe is not the sole physical reality, but merely an unimaginably tiny, almost infinitesimal, component within the vast, sprawling expanse of a much grander multiverse. Yes, each individual world, nestled within this multiverse, certainly possesses a definite beginning in time. Our own, for example, burst into being approximately 13.8 billion years ago. However, the entirety of this self-reproducing, self-perpetuating cosmic structure, viewed in its awesome totality, could potentially be infinitely old. If this is indeed the case, then we are absolved from the need to posit any singular, unexplained first cause for its existence. For a world that has always existed, for an infinite stretch of time, there is no inexplicable moment of creation that demands a prior explanation. As the eminent Scottish philosopher David Hume eloquently articulated, nothing can precede an infinite past. Every event, in such an eternal causal chain, is always accounted for by a preceding event, and this chain stretches back endlessly, without any ultimate beginning or end. But even if the world were truly eternal, stretching infinitely into the past, would that alone be sufficient to dispel the lingering, profound sensation of mystery? Jim Holt, in his philosophical exploration, contends that it would not. Such an infinite world, he suggests, is akin to a colossal railway train comprised of an infinite number of wagons, each pulling the subsequent one, yet utterly lacking a locomotive to initiate its motion. Or, to employ another evocative metaphor, it can be compared to a vertical chain with an infinite number of links, where each link meticulously supports the one below it, yet the fundamental question remains: what, precisely, holds the entire endless chain aloft in the first place? Even in the absence of a singular, ultimate first cause, the profound enigma persists. Why, in principle, should the universe exist at all? And, crucially, why, in this existing universe, are the fundamental laws of nature precisely as they are? Guess where, after such profound and far-reaching reflections, the gaze of many esteemed thinkers once again irresistibly turns. In the year 1078, the visionary philosopher Anselm of Canterbury conceived of a remarkably audacious method to logically prove the very existence of God. This ingenious formulation became known as the ontological argument, and for over a millennium it has continued to captivate, to perplex, and to, at times, infuriate thinkers across the spectrum of belief. You might recall a certain video, widely circulated, that many of us enthusiastically shared as a definitive affirmation of the logical correctness of atheism. In this video, Bertrand Russell, the brilliant British philosopher, logician, and mathematician, whose monumental contributions profoundly shaped mathematical logic, the history of philosophy, and the theory of knowledge, articulated his perspective. In his autobiography, Russell recounts a pivotal moment of intellectual epiphany. I remember the exact moment in 1894, when, walking along Trinity Lane, I saw in a flash that the ontological argument is sound. I had gone out to buy some tobacco, and coming back I threw the tin of tobacco up in the air and exclaimed, "Great Scott, the ontological argument is valid." So what precisely is the core essence of this famous ontological argument? In its most concise form, it unfolds thus: God, by definition, is the most perfect conceivable being. However, Existence in the realm of imagination is, by its very nature, less perfect than existence in concrete reality. Since God, by definition, is absolutely perfect, it therefore logically follows that God must exist in reality. As you may have gathered, Russell later arrived at the conclusion that the ontological argument, despite his initial, exhilarating conviction, was not, in fact, truly valid. Nevertheless, he famously remarked that it is often, quote, easier to be convinced that it is fallacious than to find precisely wherein the fallacy lies. For instance, one might point out that the asterisk idea of God is not, in itself, a variety of God, however imperfect it might be. Just as a painted apple, however skillfully rendered, is not a variety of an actual apple, even if it is far less nourishing. But the story of the ontological argument did not conclude there. Perhaps you also recall another widely shared video featuring a well-known personality who, with great intellectual dexterity, attempted to disprove the existence of God by invoking Gödel's incompleteness theorems. The ironic twist in this particular narrative is that Kurt Gödel himself, the very mathematician whose theorems were being cited, later discovered a method to revive the ontological argument for the existence of God, presenting it in an even more rigorous and powerful form than Anselm's original, utilizing the sophisticated tools of modal logic. In this rendition, too, however, the path remains far from entirely smooth, fraught with its own set of philosophical complexities and debates. In any event, regardless of whether a divine being exists or not, the fundamental question remains: how deeply, how comprehensively are we truly capable of grasping the ultimate nature of reality? Is there an inherent limit, a conceptual horizon beyond which our understanding can never truly extend? The prominent British physicist, often heralded as the father of quantum computation and a fervent proponent of the many worlds interpretation, David Deutsch, boldly contends that no such intrinsic limit exists. In 1985, Deutsch achieved an extraordinary intellectual feat. He rigorously demonstrated the theoretical possibility of a universal quantum computer. This hypothetical machine of unparalleled computational power would be capable of performing the work of any two-nation conceivable computational device, ranging from the familiar classical computers we use today to the more esoteric quantum computers initially envisioned by the legendary physicist Richard Feynman. Indeed, in its most profound manifestation, Deutsch suggested, such a universal quantum computer would effectively serve as the ultimate ideal machine for simulating virtual realities. The anecdote of Deutsch presenting his groundbreaking proof is rather remarkable. When a young Deutsch journeyed to Caltech to share his evidence for the existence of a universal quantum computer with Richard Feynman, who was by then already gravely ill with cancer, Deutsch began writing the initial formulas of his proof on the blackboard. Suddenly, the ailing Feynman, despite his weakened state, reportedly sprang to his feet, seized a piece of chalk, and, with a flash of his renowned genius, completed the derivation himself. For Deutsch, the universal quantum computer became far more than a mere theoretical construct. It emerged as the crucial key, the Rosetta Stone, for unlocking a deeper understanding of reality itself. Such a machine, capable of constructing and simulating any physically possible world, would, in his view, represent the ultimate and final objective of all physical knowledge. It would be a singular physical artifact that could, in principle, be built, and which would possess the astonishing capacity to describe or simulate with exquisite precision any conceivable portion of the vast quantum multiverse. In the year 2023, David Deutsch was rightly awarded the prestigious Breakthrough Prize in Fundamental Physics for his pioneering and foundational work in the field of quantum computation, a testament to the enduring impact of his ideas. Deutsch offers a compelling illustration of this profound connection between mind and reality. He points out that an astrophysicist, through the sheer power of conceptual abstraction and scientific understanding, can form an incredibly vivid and accurate mental image of a quasar, a colossal, extraordinarily energetic celestial object situated billions of light-years away in the distant cosmos. The mental picture of this quasar, which spontaneously arises within the confines of the astrophysicist's brain, possesses astonishing properties. It is not merely a superficial visual representation, rather, it constitutes a sophisticated structural model, one that faithfully embodies the very same causal and mathematical relationships that characterize the actual colossal quasar itself. Here, then, are two entities: a quasar, a gargantuan black hole actively devouring matter and spewing out jets of immense energy, and a human brain in its essence, a delicate chemical and electrical foam. These two objects are, physically speaking, as disparate as it is possible to imagine. And yet, in their deeper essence, they both instantiate, they both embody, the very same intricate mathematical relationships. From Deutsch's perspective, for this remarkable mirroring to occur, for the structures of the universe to be reflected within the structures of our minds, the fundamental laws of physics must possess a truly unique and profound characteristic. They must not merely permit such an intricate mirroring. They must, in fact, actively prescribe it. This suggests a deep, underlying harmony between the cognitive processes of the mind and the physical processes of the cosmos. However, even with this profound insight, Deutsch candidly acknowledges that it does not necessarily mean we will ever definitively uncover the ultimate answer to the question of why something exists instead of nothing. He states with thoughtful reservation, "I do not think that a complete comprehension of reality is possible. This does not mean, in my opinion, that there is a limit to our explanations. We will never hit a brick wall with the inscription, 'No more explanations beyond this point.' On the other hand, I do not think we will discover a brick wall upon which is written, 'This is the final possible explanation for everything.' In truth, both types of walls would, in their fundamental appearance, look practically identical." Deutsch further elaborates that none of our currently formulated laws of physics are, in their fundamental design, equipped to address the profound question concerning the ultimate reason for the multiverse's existence. Physical laws, by their very nature and methodological scope, simply do not engage with such teleological or existential inquiries. As Alan Sandage, the esteemed father of modern astronomy, once remarked, "Science cannot answer the deepest questions. As soon as you ask, 'Why is there something instead of nothing?' you have left the realm of science." Scientists can meticulously elucidate the intricate workings of the physical universe. They can meticulously trace the causal chains and the complex interactions between individual objects and forces within it. They can shed illuminating light upon the grand evolutionary trajectory of the universe as a whole, detailing how it progressed from one state to another, a process, as I have mentioned, that Lawrence Krauss so eloquently describes in his work. However, when the inquiry ascends to the ultimate source of reality, to the very wellspring of existence, science, by its own admission, finds itself without a definitive answer. Consider for a moment the profoundly contradictory nature of this concept, the existence of a definitive beginning for the world. When Albert Einstein meticulously completed his general theory of relativity, he was confronted with a startling and undeniable conclusion. His equations, in their raw, unadulterated form, unequivocally dictated that the universe must either be perpetually expanding or perpetually contracting. A third, static state, was simply not permitted. Yet Einstein, like virtually every other physicist of his era, was so deeply steeped in the conviction that the universe had no beginning, that it was eternal and unchanging, that he made a fateful modification to his own elegant equations. He introduced an additional element, a theoretical fudge factor known as the cosmological constant, thereby artificially rendering the universe eternal and static. This, he would later concede, under the undeniable pressure of observational evidence, was the biggest blunder of his life. The observations of the cosmos were becoming increasingly clear. We inhabit the remnants of a strange, explosive phenomenon. I understand that the idea of the Big Bang has, by now, become deeply ingrained in our collective consciousness, almost commonplace. But take a moment to consider this theory an abstraction, stripping away its familiarity. It is, from an intuitive standpoint, an almost absurd concept, one that profoundly clashes with our innate understanding of how things work. How could all of this, the vastness, the complexity, the sheer abundance of galaxies, stars, and life, have originated from a single, infinitely dense point? It is hardly surprising, then, that the British astronomer Fred Hoyle, the very individual who, somewhat ironically, coined the term Big Bang, considered this theory to be pseudoscientific. In a memorable broadcast on the BBC, he asserted, "The reason why scientists like the Big Bang is because they are clouded by the book of Genesis." The belief in the first page of the book of Genesis is deeply ingrained in the souls of most scientists. It can indeed be seen as a cruel irony that Fred Hoyle, a brilliant scientist, is nevertheless most widely known for inadvertently naming the very theory he so vehemently rejected. Once sufficient highly reliable data accumulated, strongly corroborating the Big Bang theory, scientists naturally began to grapple with the next logical question: what, precisely, preceded it? However, every attempt to peer into that primordial epoch consistently encountered a seemingly insurmountable obstacle, a conceptual barrier known as the singularity. This refers to a point in space-time where the threads of causality appear to converge and break down, where our known laws of physics cease to apply. The existence of this singularity so deeply troubled the burgeoning field of cosmology that numerous attempts were made to formulate scenarios that would elegantly circumvent this initial singularity. However, in a groundbreaking development in 1970, the physicists Roger Penrose, a name we will revisit with deeper appreciation shortly, and Stephen Hawking unequivocally demonstrated that these attempts to avoid a singularity were ultimately doomed to fail. Through rigorous mathematical precision, they proved that a singularity must lie at the very beginning of the universe. Does this imply, then, that the ultimate origin of our world will forever remain shrouded in impenetrable mystery beyond the reach of human comprehension? Not necessarily. It simply means that the Big Bang, in its entirety, cannot be fully understood solely through the lens of classical cosmology, that is, cosmology based exclusively on Einstein's general theory of relativity. Other more encompassing theories, particularly those incorporating quantum mechanics, would be required to truly unravel its deepest secrets. The American physicist and cosmologist Alexander Vilenkin, in contrast to Lawrence Krauss, emphatically insists that the universe did, in fact, emerge from an absolute nothingness. And Vilenkin is precise in his definition. Nothing is nothing. It is not merely the absence of matter, it is the absence of space, the absence of time, a complete and utter absence of everything. But how, then, can a physicist even begin to define, let alone mathematically describe, a state of such absolute emptiness? It is here that Vilenkin demonstrated truly remarkable ingenuity. Imagine, if you will, the fabric of space-time not as a flat, infinite plane, but as the curved surface of a sphere. Such a configuration of spacetime is referred to as closed, precisely because it curves back in on itself, forming a finite yet unbounded continuum. Now, envision this sphere gradually contracting, much like a deflating balloon from which all the air is slowly released. The radius of this sphere becomes progressively smaller and smaller, until, in a final climactic act, it diminishes to precisely zero. At that instant, the surface of the sphere entirely vanishes, and with it, the very essence of spacetime itself. We have, at this conceptual point, arrived at a state of absolute nothingness. Simultaneously, we have reached a precise, scientifically definable understanding of nothing. It is a closed spacetime with a radius of zero. This, Vilenkin contends, is the most complete and perfect form of nothingness that can be described within a scientific framework. It is not only devoid of any content whatsoever, it also fundamentally lacks both time and spatial coordinates. Armed with this rigorous definition, Vilenkin proceeded to perform a series of fascinating calculations. Utilizing the profound principles of quantum mechanics, he demonstrated that from such an initial state of nothingness, a minuscule fragment of energy-filled vacuum could spontaneously materialize. How minuscule, you might wonder, perhaps no larger than a mere trillionth of a centimeter. Under the influence of the negative pressure inherent in cosmic inflation, this minute fragment of energetic vacuum would then experience an unrestrained exponential expansion. Within a few fleeting microseconds, it would balloon to astronomical dimensions, eventually unleashing a torrent of matter and energy, the Big Bang itself. From a purely scientific perspective, this theoretical schema appears remarkably coherent. Vilenkin's calculations seem robust and sound. However, in a conversation with Vilenkin, Jim Holt raised a crucial objection: the bubble of false vacuum from which the cosmos supposedly sprang must, by all conventional logic, have originated from somewhere and asterisk at some point in time. Vilenkin, attempting to clarify, suggested imagining a bubble of gas forming in champagne and then mentally removing the champagne, as if this analogy might somehow alleviate the conceptual difficulty. Yet, it arguably muddies the waters further. A bubble in champagne forms over the passage of time, but absolute nothingness, by its very definition, possesses no time whatsoever. Consequently, no processes, no events can, by definition, unfold within it. But if Vilenkin's theory holds true, then paradoxically, nothingness never truly stood a chance. The very laws of physics, those fundamental principles that, in this framework, must necessarily exist outside of space and time, mandate that, with a certain non-zero probability, a universe must come into existence. Does this profound implication mean that these laws are not merely descriptive frameworks for reality, but rather possess an independent, almost platonic, existence of their own, even in the complete absence of space, time, and matter? On what mysterious tablets could these primordial laws possibly be inscribed? To this, Vilenkin offers a thought-provoking, almost theological, response. If you want, you can say that they are in the mind of God. Thus, the mathematical laws that precede the world and serve as its ultimate cause emerge as a central enigma. We seem to have heard echoes of this idea before. In the intricate realm of mathematics, nothingness actually possesses a name: zero. The concept of zero, far from being an intuitive given, was a revolutionary invention, meticulously developed by Indian mathematicians. For the ancient Greeks and Romans, the very notion of zero simply could not enter their conceptual framework. It was an alien idea to them how nothing could also be something, a placeholder, a number, a quantity in itself. Classical antiquities mathematics conspicuously lacked the numeral 0, without which it is fundamentally impossible to fully leverage the profound advantages of our familiar position-based decimal system. For instance, in our system, the number 906 elegantly signifies 9 hundreds, 0 tens, and 6 units. Contrast this with the utterly cumbersome, almost maddening, attempts to perform complex calculations within the archaic Roman numeral system, a system fundamentally crippled by the absence of this crucial placeholder. The Indian mathematicians' profound understanding of the concept of emptiness or void was significantly influenced by the subtle and intricate philosophical tenets of Buddhist thought, which had a profound impact on their intellectual landscape. Consequently, they found it remarkably easy to manipulate and operate with an abstract symbol that unequivocally signified nothingness. As for the precise historical origins of the symbol for 0 itself, the elegant, rounded cipher we use today, historians of antiquity have, despite exhaustive efforts, largely failed to conclusively ascertain its genesis. One intriguing theory, among several, posits that the symbol for 0 originated from the simple, circular imprint left by a coin pressed into soft sand, a tangible trace, a material shadow of the immaterial void it represented. Now, prepare yourself, for this next assertion might surprise, perhaps even slightly startle, you. According to Jim Holt's extensive research, a significant majority of mathematicians, he estimates roughly 2/3, hold a belief in something profoundly divine. And this belief is not necessarily directed towards a celestial realm populated by winged angels and beatified saints. Rather, it is an unwavering conviction in the existence of a transcendent world, a realm populated by perfect, eternal, and unchanging mathematical objects, the very entities that form the subject of their lifelong study. They believe in the objective reality of prime numbers, the unwavering truth of theorems, the inherent existence of intricate geometric forms, the elusive nature of the square root of -1, and so forth. More astonishingly, many of them profess a profound belief that they communicate with this ethereal world of mathematical verities through something akin to a form of extrasensory perception, a direct, almost mystical intuition. Indeed, mysticism and mathematics have enjoyed a long and intricate relationship, often intertwined at their deepest roots. It was, notably, the followers of the mystical cult of Pythagoras who are credited with the groundbreaking invention of mathematics as a deductive science. Their community was, in essence, a religious sect whose members revered numbers as a divine endowment, a sacred gift from the cosmos. All is number, proclaimed Pythagoras, encapsulating their profound spiritual and intellectual conviction. Later, the monumental philosopher Plato, deeply influenced by the profound teachings of the Pythagoreans, laid the intellectual groundwork for his own distinctive philosophy. The very word idea, incidentally, owes its etymological and conceptual existence directly to him. As I may have mentioned in a previous discussion, but which bears repeating for its profound significance, Plato observed that geometers routinely engage in rigorous discussions about circles that are perfectly round, ideal in their curvature, and about lines that are infinitely, absolutely straight. Yet, the striking reality is that such perfect circles and truly infinite straight lines simply do not and cannot exist in our physical perceptible world. Consider a simple wooden wheel. It appears round, does it not? But in truth, it is not perfectly round. It merely approximates roundness. No matter how skilled the carpenter, no matter how precise their instruments, they will never, ever be able to craft an object that embodies the absolute ideal of a circle. with a perfectly uniform radius and an area precisely equal to pi times the radius squared. Thus, every physical wheel on our planet, every imperfect rendition of circularity, is, in Plato's profound conception, merely a copy or a shadow of an ideal, perfectly circular wheel, a conceptual entity that quite literally does not exist in our perceptible, material world. The same fundamental principle applies to numbers. The number 2, for instance, in its purest mathematical form, ought to consist of a pair of perfectly identical units. Yet in the real physical world, no two things are ever absolutely perfectly identical in every conceivable respect. If such ideal entities are impossible to discover within the physical world that we apprehend through our sensory organs, if we can only ever meaningfully engage with them through the abstract workings of our minds, then where, precisely, do they reside? Plato's profound conclusion was that the objects of such rigorous mathematical reasoning must necessarily exist in a different realm altogether. An eternal, unchanging, and ideal world of ideas, or forms. He posited that our rational faculty, our capacity for abstract thought, is bestowed upon us precisely for the purpose of perceiving these ideal forms, just as our eyes are given to us to perceive light and our ears to apprehend sound. And, astonishingly, as Jim Holt's research suggests, roughly 2/3 of contemporary mathematicians concur with this profoundly Platonic perspective. Among the most distinguished contemporary Platonists, one can highlight Alain Connes, a revered mathematician who holds a prestigious professorship in analysis and geometry at the Collège de France. Connes steadfastly asserts the existence of an immutable mathematical reality, one that operates entirely independently of the human mind. Another prominent modern Platonist, René Thom, who achieved considerable renown in the 1970s as the pioneering creator of catastrophe theory, declared with conviction, "Mathematicians must gather the courage to express their deepest convictions and thus declare that mathematical forms do indeed exist, independently of the mind that studies them." Kurt Gödel, the legendary logician whose work we touched upon earlier, was a fervent Platonist. He firmly believed that we do, in fact, possess a form of perception for mathematical objects, despite their inherent detachment from direct sensory experience. "I see no reason to have less trust in this kind of perception," Gödel wrote, referring to mathematical intuition, "than in sense perception." It is worth noting, as a curious aside, that Gödel also held a belief in the existence of ghosts, but that, as they say, is an entirely different matter for another time. Many physicists, too, find themselves irresistibly drawn to Plato's ideas. Mathematical entities not only strike them as eternal, inherently real, and immutable, but they also appear to function as the very orchestrators, the silent commanders of the physical universe. How else, one might reasonably inquire, can one account for what the physicist Eugene Wigner famously termed the unreasonable effectiveness of mathematics in the natural sciences? That is to say, is it not profoundly strange that these abstract constructs, these intricate mental creations of our minds, prove to be so astonishingly precise and effective in describing and predicting the behavior of the real physical world? Indeed, modern physics, in its most fundamental expression, is simply unimaginable without the indispensable language of mathematics. If, to paraphrase the words of Galileo Galilei, the book of nature is written in the language of mathematics, then this can only logically imply that the world, at its very deepest and most fundamental level, is intrinsically mathematical. Perhaps, then, mathematics holds the key, the ultimate clue, to unlocking the profound mystery of existence itself. Among all contemporary Platonists, one individual stands out as an authentic, towering genius: Sir Roger Penrose. Please forgive me, but I feel compelled to enumerate some of his extraordinary accolades. Otherwise, if you are unfamiliar with his immense contributions, you might not fully appreciate the profound weight and significance of what is to follow, perhaps dismissing it as mere speculation from an unknown academic. Roger Penrose is widely considered among the most highly decorated mathematical physicists currently alive. His esteemed colleagues, most notably Kip Thorne, have lauded him for his pivotal role in reintroducing rigorous mathematics into theoretical physics after a prolonged period during which the two fields had, in a sense, ceased to meaningfully communicate. As I mentioned earlier, it was in the 1960s that Penrose, working in collaboration with Stephen Hawking, utilized sophisticated mathematical methods to provide irrefutable proof that the universe must have originated from a singularity. In the 1970s, Penrose developed the profound concept of the cosmic censorship hypothesis, a theory asserting that every singularity, every point of infinite density and space-time curvature, is invariably concealed behind an event horizon. This event horizon, in his conception, serves to protect the rest of the universe from the catastrophic breakdown of physical laws that would otherwise occur. Roger Penrose also stood at the very vanguard of a revolutionary new approach, one that sought to reconcile the seemingly disparate realms of general relativity with the enigmatic principles of quantum mechanics. In 1994, in recognition of his extraordinary achievements, Queen Elizabeth II bestowed upon Penrose the esteemed title of Knight Bachelor. He is also renowned for his enduring fascination with the peculiar and the impossible. Even as a student, he became utterly captivated by the concept of impossible figures, that is, visual representations of objects that, while seemingly depicted in three dimensions, defy the logical constraints of three-dimensional space. The famous Penrose triangle, for example, directly inspired M.C. Escher to create his iconic and mind-bending lithographs. Recall that memorable moment from the film Inception featuring the perpetually ascending Penrose stairs? Yes, that particular impossible staircase is indeed named in honor of him and his father, who first presented the concept of this continuous, unending ascent in a seminal paper published in 1959. And the crowning glory, in 2020, Penrose was awarded the Nobel Prize in Physics. So, this extraordinary figure, Roger Penrose, harbors absolutely no hesitation in openly declaring his profound allegiance to the teachings of Plato. In his numerous scholarly works and his engaging public lectures, he has repeatedly made it clear that he regards mathematical entities as genuinely real and as profoundly independent of the human mind as the majestic peaks of Mount Everest. Indeed, he explicitly invokes Plato in his seminal book, The Emperor's New Mind, published in 1989. He writes, "I believe that when the mind perceives a mathematical idea, it enters into contact with Plato's world of mathematical concepts. Each mathematician entering into this contact may conceive something distinct in each instance, yet communication between mathematicians is possible, precisely because each of them is directly connected to the same eternally existing Platonic world. At times, he even subtly hints that in our very own physical world, we continually stumble upon tantalizing glimpses, profound manifestations that originate from this Platonic realm." In his subsequent work, Shadows of the Mind, A Search for the Missing Science of Consciousness, published in 1994, which, like its predecessor, became an astonishing bestseller, Penrose posits that consciousness is not algorithmic. He contends that it cannot, by its very nature, be accurately simulated, or replicated by even the most powerful and sophisticated computer. Consciousness, from his perspective, is fundamentally quantum in its essence. He believes that only through a yet undiscovered, comprehensive theory of quantum gravity will we one day be able to explain how the intricate processes of the human brain give rise to this profound phenomenon. Perhaps in a future exploration, I might dedicate an entire discussion to the fascinating ideas presented in these books. However, it is important to note that many neurobiologists reacted with considerable skepticism, even outright derision, to Penrose's bold claims. The late Francis Crick, co-discoverer of the structure of DNA, famously remarked with exasperation, "His argument is that quantum gravity is mysterious and consciousness is mysterious. Therefore, it would be wonderful if one explained the other." But Penrose, in fact, aspires to something far grander, something far more profound. The very title of his book, Shadows of the Mind, carries a deliberate double meaning. On one hand, it is intended to convey that the electrical activity of brain cells, the tangible, measurable, neurological processes that we currently identify as the source of our mental experiences, are merely the shadows, the superficial manifestations of much deeper, underlying quantum processes occurring within the brain. These quantum phenomena, he argues, are the true, fundamental source of consciousness. On the other hand, the word shadows is a direct and profound allusion to Plato, specifically to his iconic allegory of the cave. This allegory describes prisoners confined in a cave, perceiving only the shadows cast by objects passing before a fire, mistaking these fleeting images for ultimate reality. Penrose, then, suggests that our ordinary perception of consciousness, rooted in classical brain activity, is similarly a shadow of a deeper quantum reality. Jim Holt, in his quest for answers, seized the opportunity to directly engage with Penrose on this very subject. Holt inquired, "Do you truly believe in a Platonic world existing above the physical world? Would not the idea of two such worlds be somewhat ontologically extravagant?" Penrose, with his characteristic calm and profound conviction, responded, "In fact, there are three worlds, and they are all distinct from one another. There is the Platonic world, there is the physical world, and then there is the mental world, the world of our conscious perception." He continued, "The interrelationships between these three worlds are, quite simply, mysterious. Perhaps the greatest enigma I am currently grappling with is the connection between the mental world and the physical. How do certain highly organized physical objects, like our brains, produce consciousness? Another mystery, no less profound from the perspective of mathematical physics, is the relationship between the Platonic world and the physical world. In our tireless search for the deepest understanding of the regularities governing the behavior of the world, we inevitably turn to mathematics. It is highly probable that the physical world is, at its very foundation, constructed upon mathematics. Penrose then elaborated on the seemingly paradoxical interactions. It would seem, for instance, that there is an interaction between our physical brains and the Platonic world. Each of the three worlds, the physical world, the world of consciousness, and the Platonic world, emerges from an infinitesimal fragment of one of the other two, and it is invariably the asterisk most perfect fragment. Take, for example, the human brain. If we consider the physical world in its entirety, our brain constitutes a very, very tiny part of it. Yet, it is the most exquisitely, most perfectly organized part. Compared to the astounding complexity of the brain, a galaxy, for all its cosmic grandeur, appears as little more than a clumsy, diffuse lump of matter. The brain represents the most refined, the most intricately structured portion of physical reality, And it is this very fragment that gives rise to the mental world, the realm of conscious thought. He continued, in a similar vein, only a small portion of our conscious thought truly connects us to the Platonic world. But this, again, is the most flawless, the most impeccable part of our mentation, the part that consists of our deepest reflections on mathematical truth. Finally, only a few select particles of mathematics within the Platonic world are necessary to describe the entirety of the physical world. But these are the most powerful, the most astonishing of its components. And from Penrose's profound perspective, these most powerful and astonishing parts of mathematics are inherently capable of creating the physical world itself. It is, in his view, the Platonic world that serves as the ultimate wellspring of reality. In Shadows of the Mind, he unequivocally states, "For me, the world of perfect forms is primary, just as it was for Plato. The existence of this world is almost a logical necessity. The other two worlds, the worlds of matter and mind, are, in essence, its shadows." In other words, the Platonic world must exist based solely on the principles of logic, while the realms of matter and mind ultimately flow forth from it as a profound byproduct. On one hand, it is undeniably fascinating to peer into the inner workings of such a magnificent intellect, to listen to his philosophical musings on the deepest questions of existence. But on the other hand, for some, all of this might resonate as rather vague, detached from any tangible reality, mere chatter about some immaterial, ethereal stuff. However, and this is where the paradox deepens, as our scientific theories become progressively more refined, more comprehensive, and more accurate, the less of that very matter seems to remain within them. The profound process of the dematerialization of nature, the gradual stripping away of its perceived solidity, began its inexorable march as far back as Isaac Newton. His groundbreaking theory of gravity, for instance, introduced the seemingly supernatural concept of action at a distance. In Newton's law of universal gravitation, the sun, without any intervening physical medium, reaches out across the vast, empty expanse of space to exert a powerful gravitational attraction upon the Earth. How this occurs, in the complete absence of any intermediate matter, was a question that deeply troubled Newton himself. He famously and humbly declared, "Hypotheses non fingo, I feign no hypotheses," admitting his inability to explain the asterisk how of gravity, only its precise mathematical description. If Newton's theories began the dematerialization of nature across cosmic distances, then modern physicists have continued this profound process, but now at the smallest, most fundamental scales of reality. In 1844, Michael Faraday, with his penetrating insight, observed that matter could not truly be apprehended directly, but only inferred through the forces acting upon it. This led him to pose a logically compelling question. Why, then, should we even postulate its independent existence? According to Faraday, the very fabric of physical reality, at its deepest level, is not, in fact, composed of discrete particles of matter, but rather of fields, purely mathematical structures defined by points and numbers. By the early 20th century, atoms, which had long been regarded as the quintessential epitome of solidity and indivisibility, were revealed to consist predominantly of empty space. And then, the advent of quantum theory brought an even more radical revelation. Their constituent subatomic particles, electrons, protons, and neutrons, were not, in fact, tiny hard balls or miniature planetary systems. Instead, they were revealed to be enigmatic packets or condensations of abstract properties, behaving sometimes as particles, sometimes as waves, defying simple classical intuition. At each progressively deeper level of scientific inquiry, that which was once considered matter consistently dissolved into pure structure, into intricate patterns of relationships. One might still protest, but so what? We don't, after all, simply fall through the floor. Indeed, two solid objects cannot, in our everyday experience, interpenetrate. However, the reason they cannot has absolutely nothing to do with some inherent, intrinsic hardness or fundamental solidity residing within the matter itself. The explanation, rather, lies deep within the realm of numbers and quantum rules. To forcibly compress two atoms together to bring their electron shells into interpenetrating proximity would require placing the electrons within those atoms into identical quantum states. And in the strange counterintuitive world of quantum theory, this is rigorously forbidden by the Pauli exclusion principle, which only permits two electrons to occupy the same quantum state if their intrinsic spins are precisely opposite. As for why electrons within an atom do not simply spiral inwards and crash into the nucleus, that, too, is primarily a mathematical problem rooted in quantum mechanics. If electrons were indeed to reside directly on the nucleus at the atom's center, we would then possess precise knowledge of their exact location, as well as their velocity, which would then be, by definition, zero. But this, in turn, would directly violate the Heisenberg uncertainty principle, which fundamentally precludes the simultaneous, precise determination of both a particle's position and its momentum. Thus, the perceived solidity of the ordinary material objects that surround us, the walls, the floor, the unyielding stones, is not a consequence of some inherent classical density. Instead, it is an emergent property, a direct consequence of the interplay between the Pauli exclusion principle and the Heisenberg uncertainty principle. In other words, all of what we perceive as hardness ultimately reduces to a pair of abstract mathematical relationships. At the most fundamental level, science, in its relentless pursuit of understanding, describes the constituent elements of reality solely in terms of their intricate relationships with one another. It largely disregards or bypasses any inherent material qualities that these elements might be imagined to possess. For instance, science informs us that an electron possesses a specific mass and a particular charge. Yet, these attributes are merely properties that enable other particles and forces to interact with the electron in a precisely defined manner. Science elucidates that mass is equivalent to energy, but it does not, and cannot, explain what energy intrinsically kilcools, beyond defining it as a numerical quantity that, when correctly calculated, remains conserved across all physical processes. As Bertrand Russell keenly observed in his profound work, The Analysis of Matter, when the inquiry delves into the true, intrinsic nature of fundamental stuff, science falls silent. It offers us only a colossal, intricately woven cobweb of interrelations, pure structure, and no discernible matter. The latest, and perhaps most radical, achievement in this centuries-long process of the dematerialization of nature is the ambitious framework known as string theory. This theory posits that matter itself, in its ultimate essence, is constructed not from point-like particles but from pure geometry, from minuscule, vibrating strings of energy existing in higher dimensions. String theory stands as the leading candidate for what is often termed a theory of everything, a unified framework capable of describing all fundamental forces in particles. It is anticipated that this theory will be able to penetrate deeper into the cosmic enigma than even the quantum cosmology of Hawking, Vilenkin, and others. For example, string theory offers a conceptual framework that might allow us to imagine reality before the Big Bang, a primordial epoch when the very concepts of space and time, as we understand them, simply held no meaning. One of the greatest physicists who, more than anyone else, stood at the very epicenter of efforts to construct such a definitive theory was Steven Weinberg. In 1979, he was awarded the Nobel Prize in Physics for his monumental contributions to the unification of two of the four fundamental interactions, the electromagnetic and the weak forces. In his illuminating book, Dreams of a Final Theory, Weinberg muses, the discovery of a final theory may bring disappointment, for nature will become more ordinary, there will be fewer miracles and mysteries. As we can gather from this statement, he did not believe that a theory of everything would, in fact, be capable of explaining absolutely everything. But what, precisely, was this part of the cosmic mystery that Weinberg suggested would remain beyond the grasp of even a final theory? From his perspective, the answer to the profound question of why any laws exist in the first place hinges critically on the ultimate form and nature of this final theory. Let us assume for a moment that this theory, when finally discovered, turns out to be structured in a manner similar to Newton's theory. Newton's framework clearly delineates between fundamental laws like gravity and specific initial conditions, the positions and velocities of planets at a given moment. Newtonian physics, for instance, offers no intrinsic explanation for the specific initial conditions of our solar system. Newton himself recognized this profound limitation and believed that these initial conditions were, in fact, established by a divine hand. If, then, the ultimate final theory were to similarly leave these initial conditions unexplained, even if it were to flawlessly account for the entire developmental process of the universe, the ultimate genesis, the very origin of the universe, would nonetheless remain shrouded in an impenetrable fog. Who or what, Steven Weinberg pondered, established these initial conditions? Einstein once famously remarked that what truly interested him was whether God had any choice in the creation of the world. In other words, is it merely a matter of pure, improbable chance that our particular universe possesses such remarkably life-friendly qualities? Or, if we possessed a complete and perfect knowledge of all the laws of physics, would we then comprehend that the universe, in its fundamental essence, simply could not be otherwise? Why are the fundamental constants of nature so astonishingly finely tuned, so exquisitely balanced, that the world possesses the potential for the emergence and development of complex life? Alter even the slightest parameter, tweak any one of these constants by an infinitesimal amount, and the entire intricate cosmic edifice would collapse like a house of cards, incapable of supporting the conditions necessary for life. Weinberg himself was visibly amazed by this apparent fine-tuning. He believed that the only plausible explanation for this phenomenon, aside from a direct divine intervention, could only be found within the framework of the multiverse. That is, a grand cosmic expanse consisting of an immense, perhaps infinite, number of distinct universes, each possessing its own unique set of natural laws and its own particular values for these fundamental constants. The vast majority of these universes, he conceded, would be utterly inhospitable to life, but a precious few, by sheer cosmic lottery, would by chance possess conditions uniquely favorable for its development. I am not claiming, Steven Weinberg clarified, that the multiverse will resolve all philosophical questions. It will merely relieve us of our astonishment that the conditions in our universe are so well suited for the development of life and intelligence. So you see, Weinberg's perspective extends even beyond the conventional understanding of the multiverse. It goes a step further. When we encounter the concept of fine-tuning, we are indeed struck with a profound sense of wonder. We are astonished, imagining it as a cosmic control panel with a multitude of sliders, each corresponding to a fundamental law of nature. We marvel at how precisely these sliders have been adjusted, how perfectly they are tuned for the existence of life. This contemplation often leads us to the conclusion that there must be many universes, in each of which these sliders are set to different, random positions. However, we often overlook an even more astonishing, a far more profound question. Why are these specific laws themselves the way they are? Why is it this particular set of laws and not something entirely different? Or, to make the thought experiment even more challenging, why are there precisely this number of laws? Imagine, for instance, a world where only half the number of fundamental laws existed, or, even more perplexing, a world where there were twice as many laws. If this idea remains somewhat abstract, allow me to illuminate it with an analogy from the realm of computer games. Consider two distinct genres, a sprawling adventure game and a complex strategy game. Both games operate under fundamentally different sets of parameters. In the adventure game, for example, you might have the ability to precisely adjust the jump height of your character. In the strategy game, however, not only is there no such parameter, but the very concept of jumping does not even exist within its mechanics. Conversely, in the strategy game, you might possess the intricate ability to manage the economic indicators of an entire nation. In the adventure game, such a sophisticated mechanic is simply not provided for. Moreover, the adventure game might unfold in a richly three-dimensional world, while the strategy game might be confined to a two-dimensional grid. In essence, the universes of these two games are governed by entirely disparate laws, fundamentally unlike one another. Yet, and this is the crucial point, both games run on the very same underlying hardware, the same physical computer. And, for that matter, so do a game of Minesweeper and a game of Solitaire. What, then, is the import of this analogy? Steven Weinberg, I reiterate, pushes beyond the conventional multiverse hypothesis that simply posits different values for the asterisk same fundamental laws. In his book, Dreams of a Final Theory, he references an even more radical idea put forth by the Harvard philosopher Robert Nozick. Weinberg writes, "But why should a final theory describe something resembling our world?" An explanation may lie in what Nozick called the principle of fecundity. It asserts that all logically possible universes, in some profound sense, actually exist, each with its own unique set of fundamental laws. This principle of fecundity, by its very nature, is not itself explained by anything further, but it possesses, at the very least, a certain pleasing internal consistency. As Nozick himself articulated, the principle of fecundity states that all possibilities are realized, including the possibility of the existence of the principle itself. Steven Weinberg found this a compelling, if deeply metaphysical, notion. Weinberg expressed this same profound idea in his dialogue with Jim Holt. If you haven't quite grasped the full implications of what such a reality would entail, allow me to elaborate. If the principle of fecundity were indeed true, then reality would infinitely surpass anything we could possibly conceive or imagine. Our own small, familiar universe would appear unimaginably modest, almost insignificant, within this boundless expanse. For, beyond our own world, there would exist all logically possible worlds. Worlds containing a single electron and a single positron, forever orbiting one another in cosmic dance. Worlds almost identical to our own, but with a subtle, crucial difference. Worlds populated by the ancient Greek gods, exactly as described in myth. Worlds fashioned entirely from cheese. Worlds where everything is, irrevocably, only red. And countless, inconceivable worlds whose properties and characteristics we cannot even begin to describe or conjure in our minds. All of these worlds, vast and varied, would exist, entirely unconnected by causal links. And, most likely, it would be utterly impossible to transition from one to another. I must emphasize again that this is an idea to which a distinguished and skeptical scientist like Steven Weinberg, a Nobel laureate, seriously considered. After his dialogue with Weinberg, Jim Holt remarked in his book on his genuine surprise at Weinberg's openness to such deeply metaphysical concepts. I wish to clarify, Weinberg was not asserting that this definitively the nature of reality. Rather, he was pointing to the asterisk possibility of such a reality, highlighting it as an interesting and profound thought experiment. The principle of fecundity, if it proves true, would offer an explanation for almost everything. Why is the world the way it is? And why do we, sentient beings, exist within it? The answer, in this framework, is simply because everything that is mathematically non-contradictory does exist. This includes worlds with fundamental laws precisely like our own, and among those, there are naturally worlds where these laws are so exquisitely tuned that the potential for the emergence of life exists. However, even within this grand, all-encompassing framework, the fundamental question, why does something exist instead of nothing, would still linger, unanswered, in the cosmic air. Because if we were to claim that, according to this principle, both something and nothing exist, then the principle itself would become inherently self-contradictory. The theory of everything, in Weinberg's view, might, however, shed light on the question of why anything exists at all. For example, the very laws of nature might dictate the asterisk necessity of something's existence in principle, thereby forbidding any true, absolute nothingness. Here, in his speculations, Weinberg once again resonates with Robert Nozick, who, in his later work, quote, Philosophical Explanations, posited that perhaps nothingness, conceived as a destructive force, might paradoxically annihilate itself, thereby giving rise to being. In this profound and perplexing scenario, absolute nothingness could not, in fact, exist, and being would, therefore, have no alternative. A fascinating paradox, indeed. But what, ultimately, of our personal nothingness, the cessation of our individual being that awaits us after death? Surely that is a very real prospect, is it not? Arthur Schopenhauer, who for many of us is primarily known as the philosophical figure whose profound, often melancholic quotations proliferate across the internet, is, as you might infer, celebrated for far more profound reasons. Schopenhauer's magnum opus, the foundational work of his life, is titled The World as Will and Representation. Conrad Waxman, a close friend of Albert Einstein, recalled, Albert often sat with one of the worn volumes of Schopenhauer, as if he were engaged in a serene and cheerful task. Einstein, in fact, regarded Schopenhauer as a genius. Rudolf Kaiser, Einstein's brother-in-law and biographer, recounted that in the late 1920s, in Einstein's study in Berlin, portraits of three men hung prominently: James Clerk Maxwell, Michael Faraday, and Arthur Schopenhauer. Charles Darwin, too, quoted The World as Will and Representation in his own seminal work, The Descent of Man and Selection in Relation to Sex. And the Nobel laureate in physics, Erwin Schrödinger, explicitly stated that his own philosophical views were directly influenced by Schopenhauer's profound ideas. Tonight's discussion has, in a curious way, echoed some of these influences. Arthur Schopenhauer was deeply shaped by Plato, with his vision of an eternal world of ideas giving rise to our ephemeral sensory world. Schopenhauer finds in this Platonic framework a fertile ground for developing his own unique ontology. Within the complex philosophical system crafted by Schopenhauer, our fundamental existence is deemed indestructible. However, Schopenhauer firmly rejected the existence of a personal God and an immortal soul in the conventional sense. He also denied the possibility of retaining individual personality, memories, or consciousness after the physical destruction of the body. In his extensive work, he meticulously argues that the very core of reality, its deepest essence, is a blind, insatiable, unconscious force, which Schopenhauer terms the will. And the entirety of the world as it is given to us through our sensations and perceptions is nothing other than the embodiment, the external manifestation of this fundamental will. The will, Schopenhauer writes, is the very heart, the kernel of all particulars and also of the whole. It manifests itself in every blindly acting force of nature, but it also manifests itself in the deliberate activity of man. The great difference between them concerns only the degree of manifestation, but not the essence of what manifests itself. You might reasonably object, what an absurd notion! In animals and humans perhaps, but how can a will manifest itself in a mere piece of stone, serenely drifting through the vacuum of space? Yet, Schopenhauer's vision is far-reaching. Even a seemingly inert piece of rock, he would contend, exhibits a tendency towards resistance. Resistance to internal disintegration, resistance to external forces. One must exert a definite, measurable effort to alter the state of this stone precisely because it possesses a fundamental impulse or striving to maintain its form, its direction, and its velocity. One could even extend this concept further, and perhaps somewhat poetically, considering that the greater a mass, the more intensely it locally slows down time. The stone, in its very presence, warps space-time. By attracting other matter, it seeks to slow down time as profoundly as possible, thereby carving its path into the farthest possible future of the universe. And that which we casually refer to as gravity is, in this profound sense, simply the embodied striving of objects to exist for as long as possible. This will, in Schopenhauer's expansive philosophy, is the very force that moves and invigorates the plant, that gives form to the crystal, that guides the magnet towards the north. It is the force that manifests as a shock upon the contact of dissimilar metals, and it is the force that, within the very substance of matter, expresses itself as repulsion and attraction, as separation and cohesion. And finally, and most powerfully, it is the force that we perceive as gravity, so mighty throughout all matter, perpetually drawing the stone towards the earth, and the earth towards the sun. And man, the conscious individual who perceives and comprehends reality, is nothing less than the representation of this universal will, the will's own act of self-cognition, its way of experiencing and understanding itself. The will, in its fundamental essence, cannot be destroyed, for it is the foundational, primordial force that brings forth the universe in its entirety, and humanity as a particular manifestation within it. Therefore, after the death of the physical body, the will simply finds itself embodied in a new intellectual sheath, a new form of existence. Thus, according to Schopenhauer, true non-existence, absolute nothingness, simply does not exist. As for the individual consciousness tied to the physical body, Schopenhauer argued that it is, in effect, perfectly and entirely interrupted every single day by the advent of sleep. Deep sleep, while it endures, is utterly indistinguishable from death. It differs from death solely in its relation to the future, that is, by the expectation and reality of awakening. Death, then, is merely a profound sleep in which individuality, the unique constellation of our personal ego, is forgotten. All else, however, awakens again, or more accurately, it never truly slept to begin with. Therefore, for those individuals whose lives bring them contentment, whose existence, as it is, fully satisfies them, and who, in every conceivable way, affirm its value, they can, with serene confidence, regard their existence as infinite. They can banish the fear of death as a mere illusion, a baseless apprehension instilled by the ridiculous fear of one day losing the present, a fear that, in its very essence, deceives them with the phantom of time. This, I think, is a beautiful and deeply insightful idea, and an intriguing method of confronting and denying one's own mortality. Although, it must be acknowledged, Schopenhauer himself, speaking with his characteristic candor, did not, by any stretch, consider the predicament of eternal being to be an inherently good one. Indeed, after death, he would have expressed a clear preference for a well-deserved, blissful nothingness. Thank you deeply for joining me on this expansive journey into the profound. May your thoughts drift gently now, as the concepts we've explored recede into the soft shadows of your mind, guiding you towards a deep and restorative sleep.